there, and welcome to this explainer. Look, if you're tuning in right now, I'm guessing it's probably pretty late. Your desk is probably completely covered in eraser shavings, and you're staring down a circuit analysis assignment that feels, well, entirely overwhelming. If that's you, I want you to go ahead and take a deep, slow breath. Maybe grab a warm cup of tea or coffee, and just let your shoulders drop. Today, we're going to look at the source material for your coursework and untangle one of the absolute most intimidating concepts in electrical engineering. We are going to take what feels like absolute chaos and transform it into total calm simply by changing our perspective. We're going to demystify the phasor.
So let's start with a feeling I think we all know way too well. Have you ever felt totally overwhelmed trying to keep track of a bunch of moving parts that just refuse to sit still? I mean, imagine trying to measure the exact height of a spinning bicycle wheel valve while someone is literally writing it past you. It's exhausting, right? Well, that is exactly what it feels like to analyze alternating current circuits using standard time-based mathematics. You're constantly trying to pin down voltage and current while they are endlessly fluctuating, rising and falling, second by second. It creates an enormous amount of mental friction and anxiety because your target is literally always moving.
Okay, let's dive into this. What we're visualizing here, this overlapping, tangled mess of waves, is basically anxiety drawn on a graph. Our source material calls this the time domain. We've got two overlapping sine waves here, one for voltage and one for current. They're just oscillating back and forth across that horizontal time axis. And not only are they constantly changing values, but as you can see, they are totally out of sync. One hits its peak, and then a split second later, the other one does. Trying to calculate anything useful here means you have to somehow juggle these two shifting waves simultaneously. It's practically the visual definition of stress. And honestly, the stress definitely doesn't stop with just how it looks. Because these waves are constantly in motion, trying to deal with passive elements like inductors and capacitors in this time domain means you're stuck doing really messy calculus. Just look at the mathematical relationship between voltage and current. For an inductor, the voltage is proportional to the derivative of the current. For a capacitor, you're dealing with integrals. So not only are you tracking moving targets, but you're also forced to do heavy, complex calculus just to figure out what a basic component is doing at any given second. No wonder it feels so incredibly frustrating.
But what if I told you there's a way out? Seriously, it's just a simple shift in perspective. We do not have to stay trapped in this exhausting reality of the time domain, where everything's moving and we're drowning in calculus and trig. Instead, we can step into what's called the frequency domain. The frequency domain is this peaceful, frozen alternative. Instead of tracking a wave as it endlessly moves through time, we freeze it. And by freezing it, all that terrifying calculus magically turns into simple algebra, and all those complex overlapping waves turn into basic geometry. It's literally like pressing the pause button on the universe.
And the tool we use to actually press that pause button? It's called a phasor. Now, by definition, a phasor is simply a complex number that represents the amplitude and phase of a sinusoidal wave. But let's strip away the heavy math jargon for a second, okay? Think of a phasor as just taking a freeze-frame photograph. If that alternating current is a wildly spinning wheel, the phasor is a high-speed snapshot taken at the exact moment time begins, at t equals 0. It captures everything we need to know about that wave without forcing us to watch it spin. It stops the constant motion so you can finally catch your breath and just look at the picture. Now, what's really interesting here is how beautifully simple this snapshot actually turns out to be. Notice how all that chaotic, wavy motion from before has been reduced to just a single straight arrow. That one arrow captures the two most important things about our wave at our freeze frame moment. First up, the length of the arrow represents the wave's peak amplitude, basically how strong the signal is. Second, the angle of the arrow compared to that horizontal reference line tells us its phase, which is essentially where the wave was in its cycle when we snapped the photo. And that's it, length and angle.
So here's the absolute game changer. What happens to our math when we use this snapshot? Let's compare an inductor in both domains. Over in the time domain, we've got that super stressful differential equation we saw earlier. Voltage equals inductance times the derivative of current. Yikes! But over in the frequency domain, using our phasor form, the derivative vanishes entirely. Poof, gone. It is replaced by simple multiplication. The voltage phasor simply equals the current phasor multiplied by j omega L. We've literally traded exhausting calculus for straightforward middle school level multiplication. That is the true power of this perspective shift. Let's put this into perspective with a relatable metaphor. Working in the time domain is kind of like having two different alarm clocks going off in your bedroom at slightly different times. They're totally out of sync. It's loud, it's overlapping, and honestly, it's just incredibly stressful to deal with.
But working with phasors in the frequency domain, that is like walking over to a quiet desk, pulling out a ruler, and just drawing two simple silent arrows on a piece of paper. You are capturing the exact same system, but you've completely removed all the noise and all the panic. And this brilliantly illustrates the ultimate relief you get when you need to combine multiple signals. Before, you'd have to bust out those massive, grueling trigonometric identities just to combine overlapping sine waves. I mean, nobody wants to do that. But with phasors, you literally just draw arrows. To add two waves together, you take the arrow for the first wave and you draw the arrow for the second wave starting right at the tip of the first one. Just simple tip-to-tail geometry. The resulting arrow from the start to the finish is your combined wave. It is brilliantly simple, it's visual, and most importantly, it's calm. So the next time you're staring down an intimidating alternating current circuit, I want you to run through this low-pressure checklist. No panicking allowed, okay? You just need to translate the problem. Step 1. Look at the sine wave and find its peak amplitude. Bam, that is the length of your arrow. Step 2. Find the phase angle. You know, that little degree measurement sitting right next to the time variable? That's the angle of your arrow. Step 3. Just draw the arrow on your complex plane. Once you do that, you are safely out of the chaotic time domain, and you can solve the entire circuit using nothing but basic algebra and geometry. I really want to leave you with this thought today, because, well, I know exactly how easy it is to look at a new math concept, especially complex numbers, and feel like your professor is just piling more useless work onto your plate. But please remember this. Phasors do not complicate the math. They freeze the chaos so you can finally catch your breath. They aren't an obstacle. They're a tool designed entirely to rescue you from the overwhelming nightmare of tracking moving waves and calculating endless derivatives. They literally exist just to make your life easier. So, as you close your books tonight, or maybe move on to the rest of your study session, carry this feeling of relief with you. Take a step back and ask yourself, what else in your coursework, or honestly even in your life, could be simplified just by pressing pause, freezing time, and looking at the problem from a calmer, more static perspective? Sometimes the hardest problems don't actually require more effort. They just require a different, quieter angle. Thank you so much for joining me for this explainer. Stay curious, take a breath, and happy studying.